Hello everyone, my name is Kaveh, coming to you from Hawaii, where it's another beautiful day in paradise. Bonus points if you get that reference. So this is lesson number 4. We're going to be doing some more investigations of playing with graphics in 2D and OpenGL using Common Lisp. Let me start by kind of trying to elucidate why I'm doing this. For me, the point of these lessons is not necessarily to teach you the language in detail, syntax, and so forth, and so on. It's to show you how we work in Lisp, or I should say how I work in Lisp. I shouldn't generalize. When you look at different programming languages, one of the arguments is always, oh, they're all Turing complete, so they're equivalent. Well, anybody who does programming knows that's kind of a useless thing to say. But if you make a spreadsheet and you say this language has closures, this language has macros, this language has list comprehensions, this language has monads, that doesn't really tell you that much or help you that much, because you can inevitably always work your way around those things if you really want to. But what I'm trying to get across is that there's a certain interactive way of working in Lisp, which is due to the various features that Lisp has, and it's not any one feature. It's a combination of all the various things that they were smart enough to put into the standard back in the 80s that give us what I think, in my personal experience, is the most fluid and seamless and painless and pleasant programming experience I've ever come across compared to other languages. So I'm hoping to get some of that idea across, and we'll dig into a couple of little features that help in that. The first one we're going to talk about maybe today is restarts. So in most languages, if you encounter an error, an exception, your program crashes, it dumps core. If you're lucky, you have a debugger like GDB or something, or it puts you in some kind of special debug state, and then you can look at the backtrace, maybe print some local variables and try to figure out what happened, and then exit the debugger, go back to your source file, modify it, link it, compile it, link it, run it again. Do all the same actions you did to get back to the previous state where the crash happened and see if it made any difference. Lisp has a thing called restarts. First off, when you crash in Lisp process, it doesn't dump you out into a debugger. It stays in the environment that you're in and shows you the current state. So I should not say that, that's not correct. You do go into a debugger, but the debugger is still running in your live environment, in your live executable. So you have access to all of the environment that you have when the exception occurred. And you have all the power of your programming language to investigate what went wrong. And this is the kicker, you often are able to basically fix the error and resume execution, which is very unlike some other languages. For example, let's just start with a simple example here. If we just say add 1 to my variable, okay, so the program technically crashed, but I'm not kicked out of my environment, I'm still here, and it tells me my variable is unbound. And then what it does, actually, let me do this. Let me do this with Control-C, Control-J. I didn't want to just compile it because I wanted to evaluate it. So down here in the REPL, you can see that it's got the expression that I tried to evaluate, and then it tells me unbound variable, my variable. And then we have restarts. So we have the backtrace and everything like that, but we also have restarts. And these give me things I can do to basically resume execution. So for example, one of the things I can do is I can specify a value of my variable to use at this time. So I hit the 1 key, and say down here it prompts me specify a value of my variable to use at this time, and I hit it 3, and it popped me out of the REPL. Let me go back in there. So you can see that I input 3, and it returns the value 4. So I've basically recovered from a quote crash unquote, and this is very um, obviously useful, especially if you're doing interactive development. When I'm working on my 3D graphics project, which there is another video about in my YouTube account, I will go a week or longer without ever restarting Common Lisp. I'm basically constantly in the same Emacs environment. I'm in the same REPL environment, in the same Common Lisp environment, same graphics environment, and I'm just adding classes, I'm compiling files, I'm modifying methods, I'm testing things. And to be honest, the only times I have to actually restart my process is if the crash is somewhere down in the MacOS Objective-C stuff or in the OpenGL code that leaves it in some kind of confused state. And that's sort of out of the Lisp world. Until we have proper Lisp machines again, where everything is Lisp down to the bare metal, that's something we're going to have to live with. So let me give you another example. If I have an undefined function, so I tried to call this function called myTriple with argument 5, and it says it does not exist. So one of the things I can do is I can just say retry applying it. But before I retry applying it, let me just pop back into my buffer and go down here, and I have a definition for myTriple, which is incorrect because you multiply by 3, not 2. And I recompile it, or I just compile that file, that function into my environment. So myTriple has been recompiled. I go back to my debug environment, and I simply say 0, option 0, retry, apply myTriple to 5. And it does that, invoking the restart, retry applying it, and we get the answer 17, which is correct. So this is just a little aside to illustrate one of the many features that make Lisp interesting and so rapid to develop in. I have this feeling, it's a suspicion on my part, that the speed of development is tightly related to how fast you can iterate on your ideas and how long you have to wait before you can see your ideas on the screen. And in both of these cases, Common Lisp does a really good job. There's no waiting for compiles and links and things of that sort. And you can, if you have an error, you can recover from it and carry on and not have to, spend 20 minutes trying to go back to the same state you were in, especially if you have a user interface. And you don't remember what exactly you did to get into that particular crash position. All right, pardon me while I take a sip from my comically large cup. Especially given the wide-angle lens on this laptop, it makes the mug look way bigger than it is. All right, let's get back to our 2D graphics. Here we have a bunch of methods that we have. We had translate by, rotate by, scale by that incremented the translate, rotate, and scale values. Now I just create some utility ones that you can directly say translate to, and it sets it to that particular point. Doesn't increment the current point. So it's useful for some things. So I just evaluated that region. So it put those in my world. Now let's talk a little bit about, so far we've had polygon shapes which have a list of points. And that's basically an explicit representation of geometry where you literally store every point. And then when you render it, you just call OpenGL and it connects those points for you into a polygon. We can also have what's called implicit shapes, where it contains some information such as a size. If I have a marker shape, it just contains a size value, and then it contains no geometry in itself. But the draw method is specialized to draw a certain thing based on that size. So it draws a plus sign based on that size. It draws a red, this is red, plus sign, just calls GL lines, which takes pairs of points, and then, draws a vertical line from YS to Y minus S, and a horizontal line from XS to X minus S. And So I'm going to be compiling everything in this file as we go along because I have cases where I'm introducing errors on purpose and want to recover from them and show you how those things work. So I can't compile everything ahead of time. So if we basically create a marker shape, we see here a little plus sign that's red. So we've put the description of the shape into the draw method and not necessarily in the shape itself. So this has, certain advantages or certain cases where you want to use implicit method. For example, if you're rendering a million spheres, you don't want to be saving points on the spheres and so on and so forth. You just want to store a radius and a location, perhaps, and then put all that information for the million spheres into one draw method and let it do all the drawing for you at render time, or all the computation of the points at render time, perhaps. So, and now, if I want to translate this shape, I basically am doing a little bit of a translation to the right and upwards, a little bit of rotation 15 degrees, and scaling it up by 1.5. So if I compile this expression, you can see the plus sign moves, rotates, and gets bigger. And I can then do things like, say I want to put 100 of these markers in a scene. So I just loop over I from 0 to 99, adding to the scene, and I will make an instance of the marker shape of a random size between 0.05 and 0.2, and then I will translate it to some random point between minus 0.8 and 0.8 in x and y. So they stay kind of more or less on the screen. So if I do that, we have 100 markers on our screen. If I do it again, obviously we have different random numbers, so it changes. And now what I can do is I can loop through all the shapes in my scene, and I can rotate by 20 degrees each of those markers. So they're all rotating as we go along. So this then gives me an idea that one of the things I want to do is basically be able to specify a list of points and have shapes created at that point, at those points. So we think of this function called makeShape at points. It takes a shape function that creates a shape and then a list of points. And we loop over the points. We create a shape and assign it to variable s, local variable s. So fun calls shape fn, calls that function. It has no arguments. So the function should not have any arguments. It's just what we call a thunk, which is a lambda with no arguments. And then we translate, using our new translate to method, that shape to that point, and then we add it to the scene. So let's define this, compile it, and let's then take a hexagon shape, a small hexagon shape, and put it on the points of a circle with 32 points. So this is our hexagon, and if I do something like, for example, let's say I want to have 16 points on my circle, I recompile it, and you get 16 points. So again, you can see how quickly you can try ideas out and test things out and make sure things work. Let's try it, for example, here by putting the same thing, the same hexagons, on a sine curve. So we're going to make a sine curve shape with 32 points. And one of the things we're going to do here is, if you remember, the sine curve went from 0 to 1. And we want this to be kind of centered from minus 0.5 to plus 0.5, so it looks more visually pleasing. So when we get the points from the sine curve, we do a map car, which, if you remember, was basically mapping over a list and returning the results of a function that basically adds or subtracts 0.5 from the x value, so it centers the sine curve for us. So now if we do this, we get this shape, which is centered in y. And so once we have that idea, that we can have a utility that puts shapes on points for us, we can then rewrite that in a slightly more Lispy way if we want to. So this is the initial definition where, it's kind of very straightforward. You can do this structure in any language, right? Just loop over the points, bind a temporary local variable, do operation 1, do operation 2. But just for fun, I decided to like rewrite it in a slightly more Lispy way. Um, so mapc is the same thing as mapcar, except it doesn't return its results. We don't particularly care about the results of um, this computation. So there's no point in wasting memory and time by building a list of the results that will get never used. But it does the same thing. It maps a function over a list. So we gave it the same function to create the shape, same list of points, and it does the same thing. So it's a translate to of the add shape to the scene of the fun call of the shape function and translate that by to P. So we had made taken care that when add shape was defined, it basically returned the shape. So now we can use that as an argument to translate to. So if we redefine this and we try it again, perhaps on a spiral this time, we can see that it is working for us. All right, time for another sip. Okay, let's talk a little bit now about polymorphism and generic functions. So polymorphism is sort of also called multiple dispatch or multi-methods, is the ability to dispatch on more than one argument in a method. So for example, in lesson 3, we had the point multiply methods that had two signatures, 2 points or a point and a scalar number. Now in Common Lisp, when you define a method, it actually creates a generic function which then stores the methods inside it, and when you call it, it looks at the signatures of the arguments that you're passing it, the types of the arguments that you're passing it, and decides which of its methods actually gets invoked. So if we look at the type of the function p star, we can see it's a standard generic function. So we didn't actually define any generic functions explicitly, but when you create a def method in Common Lisp, it automatically creates a generic function that's a wrapper for that method. And if we look at the class of it, it's a standard class called standard generic function. Now, because the Common Lisp object system is programmable and extensible, which is very unusual in programming languages, you can basically do things like subclass generic functions and make them do other things than what they're basically programmed to do. So you have a thing called the Metaobject protocol, where you can redefine the behaviors of generic functions. You can subclass generic functions and have your own generic functions that do other things. Here, if we look at describe the generic function p star, you can see it's got a name, has an arg list, two things, and basically you can see it contains two methods. It contains a method that has a signature point number and a method that contains signature point point. And if I inspect it, let me pop that up here. So we can see in the inspector that my generic function has two methods, but also interestingly, you can see the disassembly of it. So people always say Lisp is a very high-level language, you can't do any low-level stuff. That's usually not the case. If you really want to, you can do all kinds of stuff, but I'm not really an assembly programmer. I had some limited exposure to assembly programming back in the PS2 days when I was working at Square in Honolulu on the movie Final Fantasy: Spirits Within. We got some of the very first PS2 dev kits in the US, and we actually took a bunch of our movie code and recompiled it and reported it to the PS2. So I remember basically programming the VU1 vector unit and implementing, amongst other things, Perlin noise on that, and sort of getting a field of grass that was blowing in the wind with Perlin noise on a VU1. So that was pretty much my only exposure to low-level assembly programming, and it was a lot of fun. Sorry, that was just a little trip down memory lane. All right. So our scatter shapes function is just a type function. It's not a generic function. It's a regular old garden variety function. But we actually want to redefine it as a generic function because we have some ideas. Good programming languages instill new ideas. So if you want to, you can explicitly define a generic function and takes a shape function and some locations. And if I compile this, now what you see is basically we're going to encounter a quote error, unquote, an exception. Because it says the function scatter shapes is defined as something other than a generic function. So within our environment, it's already a regular function called scatter shapes. And you can't have a regular function and a generic function with the same name. But it's not a big deal. We don't have to exit our executable or start the program and exit and change the source file and recompile and relink and resume operation. You just tell it to try to remove any global non-generic function or macro definition. There we go. Now, if I look at type of scatter shapes, it's now a standard generic function. So not only can I interactively live in my world redefine a class, add new methods, I can even change the design of my code by doing things like deciding that this function should be a generic function. And if we want to inspect it, one of the things we see here is basically it has the assembly. But if you look here, it has no methods because we haven't defined any methods for it yet. We just defined a generic function, which is basically a wrapper. So now, let's start defining some methods for it. Let me move this a little bit out of the way so you can see the graph screen as well. So we want to define a number of methods for this generic function called scatter shapes. The first one takes a list of points. This is the one we currently already had as a regular function. And it does the same thing as it did before. So if I compile this, and if I reload my inspector window, we can now see that it actually has a method scatter shape. And that method scatter shape has specializers. And those specializers are the class T, which is a superclass of all classes, i.e. any type, because I did not specify a type for a shape function. I could have. And a built-in class list. So that's this particular method. And if I run it, say let's just give it 3 points and create diamonds at those points, we have our 3 points. So this works. Now, before I kept scattering my shapes on shapes and then having to get the points of the shapes. But if we can just do that directly, that'll save us some time. So if the second argument is a polygon shape, all we do is we just take the points of that shape directly. So if I now compile this function and create the little diamond shapes on a circle shape, oops, I just hit Control V twice instead of Control C, pardon me. We were here. So we have our diamond shapes on a circle. And if we refresh our inspector window, we now see that our generic function has got 2 methods, right? Because one basically takes a list of points, one takes a polygon shape. And let's define a third method as well. Let me move this comment up here so it's more clear. So the other thing we can do is basically, instead of giving it a list or a polygon shape, just give it a function. And this is points fn of type function. And it'll just call that function, and then that function's job is to return points for us. So if I compile this function, and then I go down here, and this thing basically just as a function creates an empty list of points, loops 20 times, pushes a fresh point between -1 and +1 in x and y onto our points, and then returns our points. So we run that, and if we run it again, we're going to get different random points. It's basically 20 points that are spread across the screen. And again, refresh our method, our function, our generic function, and we see that now it has the 3 standard methods. So, and here we can see that these methods, what their signatures are. So T basically means anything untyped, so to speak, not specified. And then you have a function version, a polygon shape version, and a list version. Okay. So, time for another little sip. I seem to be quite thirsty today. Very tasty. Decaf coffee, if you're interested in knowing. All right. So now let's continue with our investigation, and let's say, oh, let's make a grid of points. So we want to create a grid that's got n points in x and points in x and x points in x. Ooh, maybe I should have caffeinated coffee. Nx points in x and ny points in y, and goes from a low bounds to a high bounds. So it's basically a rectangular area of space that's going to fill with points. So we loop through the x points, calculate the factor, calculate the x coordinate, loop through the y points, calculate the y factor, y coordinate, and then we push the point x, y onto the list of points and return the list of points. So we evaluate that. And if I just want to make, say, a 3x2 grid of points here, just to test it, I can just do this and I can see my points. And since I modified the print object method on my points, I can see the coordinates when they're displayed. So I can see I've got 6 points and the coordinates look correct. So now what we're going to do is we're going to use this grid points thing and with scatter shapes and create a grid of shapes for us. So here we have a 6x4 grid of shapes between minus 0.8 plus 0.8 minus 0.4 plus 0.4. So that's this rectangle in our view. And we can then do the same thing with some squares, for example, different numbers of parameters. And so this is creating a 14x7 grid of points in the same space between minus 0.8 and plus 0.8, minus 0.4 and plus 0.4, and it's scattering squares on there. Now we can go back to our old friend randomized points and say if I take all and then our little macro for scene shapes. So for all the shapes in the scene, it's going to randomize the points on that shape. So you can see how as I keep compiling this function, it keeps executing it, and you get more and more random variations. I can also basically make random shapes within there as well. So what we're doing here is we're basically, for the shape function, we're telling it to make a circle of a certain size, but for the number of points, I'm varying between 3 and 16, and we take the floor of it because it needs to be an integer number. So if I do it again, we'll get a different distribution of shapes, but all of them have between 3 and 16 points, or perhaps 3 and 15. I'm not sure exactly where it stops. So the next function we're going to do is random points. Random points just take the same bounds information and just takes a number and just create a bunch of random points in that space. It doesn't have to be on a grid. So again, same thing we do. We loop over n times, push our new point, which is randomized between those values, the bounds, onto points and return points. And if we basically try that, let me just do that here. So we have 100 markers that are just being placed around the scene. And if I recompile it, we get different markers. Now, let me introduce another little concept in Lisp, which is, I think I mentioned previously that Lisp is sometimes, pigeonholed as being a functional programming language, or, um, something of that sort, and it's definitely not true. And Lisp is really an everything language. You can do almost anything that you can do in programming in Lisp. Um, so I wanted to introduce this feature we have in Lisp called a loop macro. Now we have seen do times and do list, and there are other things as well, other iteration constructs and so on. But loop is basically the mother of all iterators. It's a macro, like almost all the non-function features in Lisp are macros. And people love it or hate it. I'm kind of halfway in between. I don't use it super often. I prefer sort of the specificity of do times and do list and so on. But if you're doing anything complicated, looping over multiple lists or lists and arrays, and you have to do more complicated operations, it is very flexible and very useful. So, I mean, I give it the temptation once in a while and I use it. And I just wanted to show you the difference here between, so these 2 points, these 2 functions here, random points up here and random points down here, do the exact same thing. So what the loop macro is doing here is basically it takes certain keywords. So for I from 1 to n, it's almost English-like in what it does. And I just say collect these random points for me. I don't have to create my own list of results and return it and push things onto it and so on and so forth. And basically, loop simply loops over here, executes this clause, this expression, collects the results of this expression into a list, and then as I exit the loop, it returns that collection for me. So if I compile it, and I run it here again with the new definition, it is basically identical. Now, something a little bit scary. Let's look at the macro expansion of this loop macro. So here is what loop is doing behind the scenes. We're not going to go through this in any kind of detail, obviously, because it's way too complicated. But it's declaring a local variable called I that starts with an initial value of 1. Goes through, you have the loop body. When I is greater than the loop limit value, then it goes to some marker. Otherwise, you can see it creates a list of my expression here, which is creating the point, and then does other things. And finally, it returns the loop collect answer, which I'm assuming is a list it generated to store the results in. But the point of me showing you this is to show you that a lot of the features in Common Lisp are defined using macros. And since we have access to macros, we have pretty much the power to modify the language in the same way that language designers did. And this is really a mind-boggling thing where you don't, if you want a different kind of iteration loop or something like that, or different kind of conditional, you can program it using macros, and it'll be seamlessly incorporated into the language, and you can just use it as if the standards committee had, after 2 years of debate, decided to put that functionality into the language for you, but you can just define it yourself with a macro. So also, just for fun, I decided to take the diamond shape, random diamond shape, and do that as a loop macro as well, just to show you how simple and sort of readable and legible and English-like it is, which is pleasant sometimes, especially if you start like looping over multiple lists in parallel and so on. You say for I from, or 1 to 20, and then for X in this list, and for Y across that vector, and so on and so forth. So a couple of other little things just to finish up with, a couple of examples. Let's do something where basically we're going to scatter some shapes randomly 300 points, pretty much across the screen from -0.9 to +0.9. And we've done that before. We're going to do little triangles. But what we're going to do then is we're going to loop through all the shapes in the scene, and we are going to scale them by their distance from the origin. So we take the translate of the transform of the shape, which is the point of its location, take the magnitude of that. So at the origin it's 0, at the edge of at the borders of the screen it's 1. Or subtract that from 1, and then we scale the triangle by that. So if we do that, we see that the triangles in the center of the screen are larger because they're being scaled by 1 or close to 1. And they get scaled by 0.5, and then they scaled by essentially 0 down here. Now, as a final little fun note, if your eyesight is good and you're eagle-eyed, or if you're viewing this at high definition on YouTube, you might notice that some of the triangles at the corners are upside down. Why is that, you might ask? Well, they are actually further away than 1 unit from the center of the screen. So they've been actually scaled by a negative number. So if I superimpose a circle of radius 1, diameter 2 on the screen, you can see that anything outside of this thing has been scaled by a negative number, and therefore it appears upside down. So that's a fun note to leave this lesson on. Hope you enjoyed it, and I will see you again in lesson 5. Thank you. Bye.